This is lesson 8.1, Simplify Expressions with Roots. The learning objectives are to simplify expressions with roots, estimate and approximate roots, and simplify variable expressions with roots. Now, we're going to talk about roots for the next 5 lessons, 8.1 to 8.5. We're going to build your skills and make you aware of things you never knew existed. But to start, I'd like to say a root has a cooler name, and that name is radical. All right, so when we talk about radicals in this class, we are talking about roots. All right, and I'm going to use those terms as synonyms. They're going to be used interchangeably. Now, you're most familiar with square roots, and I'm going to make sure that you learn about cube roots and fourth roots and fifth roots and beyond that today, okay, in this lesson. But we're going to start with square roots, and here's a definition. For a non-negative real number b, the square root of b is the principal non-negative square root, denoted the square root of b. The square root of b equals a means that a squared equals b, and a is greater than or equal to 0. I'm going to help you make sense of this using the perfect squares and perfect cubes that you've learned in past lessons. All right, so we've made sure that you have learned your perfect squares all the way up to 16 and your perfect cubes all the way up to 10. And please pause this video and do a refresh if you need to recall these values. We're going to use them often in the coming 5 sections. Great. So we know that when we take a number and we square it, it equals, this larger number, like 4 squared is 16, or 13 squared is 169. So square rooting is doing the opposite. Okay, so it's the inverse operation of squaring. So if I had 196 and I take its square root, it takes me back to 14. If I have the square root of 121, that gives me 11. If I have the square root of 25, it gives me 5. So square rooting is the inverse operation of squaring. Now, if we think about cubing, what would the inverse operation of cubing be? We're going to talk about it shortly, but that would be cube rooting. So you have to know these perfect cube values well, because when we cube root them, they send us back to the smaller number again. So the cube root of 512 is 8, and the cube root of 125 is 5, and the cube root of 27 is 3. All right, so we need to know these numbers on the right and how they can be turned back to these numbers on the left. Great. Going back to our lesson, let us dive into some examples. And example 8.1 says simplify the square root of 144. So you know that 144 is 12 squared. That's one of your perfect squares on the list. Okay, so the square root of 12 squared, that's equal to 12. Great. Now, if there is a negative in front of the square root, like in this case, okay, ignore it for a second. Just think about what the square root of 256 is, and then we'll apply the negative outside of it after we find that square root of 256. Now, 256, that is 16 squared, all right? So that I'm going to turn 256 into 16 squared in my brain or on paper. And then I say, well, the square root of 16 squared is just 16, but there was a negative in front, so my final answer is negative 16. Now, if there's a negative outside of the square root, that's okay. We just put that negative for our final answer, and we're good to go. Great. So now it might make sense why it's important to know your perfect squares. See, like 144 and 256 in your brain, you're going here and you're saying, well, the square root of 144 is 12. The square root of 256 is 16. Great. All right. What if I'm asked to simplify the square root of negative 169? Now, there will be alarms going off in your brain because the negative is now inside the square root with the value. Okay, so if the negative sign is inside the square root with the value, then the answer is there's no real solution. So be careful with the negative sign, because if it's outside of the square root, that's fine, right? Outside of the even root, yeah, just put it on after you answer the square root's value. But in this case, the negative sign was inside the square root, and so there's no real solution. In fact, in the past, you may have learned about imaginary solutions. And so it would be an imaginary solution, but we're not going to worry about that just yet in this course. Cool. Moving on to this next option, it says the negative square root of 81. Now, in this case, the negative is in front of the square root. Awesome. So we're just going to answer this as it's going to be the negative of the square root of 9 squared. Okay, so 81 is 9 squared. The square root of 9 squared is just 9, but I had the negative in front, so this is my answer. Cool. Now, I want to tell you all something about square roots. There's something invisible. It's called the index of the root. And for a square root, the index is invisible. It's a 2, and I'm going to make it appear in all of these cases that we've done. You see, there is an invisible 2 right there. I just made it visible so you would see it. We're taking the square root, okay? And the type of root is given in this corner of this radical sign, okay? So the sign that we have right here, this is called the radical sign. This is the index value, which happens to be 2. We got a square root. Well, what if we're not dealing with square roots only, right? We know now that there are more types of roots, okay? Like square roots undo squares. They're inverse operations of squaring. What about cube roots? Cube roots are the inverse operation of cubing. Fourth roots are the inverse operation of raising to the fourth power, etc. And so here's a general statement about roots or radicals. The nth root of b is the number a such that a to the n equals b. Now, if n is even, a is non-negative for b is greater than or equal to 0, and if n is odd, a can be negative if b is negative. All right, what are we talking about nth root here? Well, our index, that thing that goes in the corner, can change from 2 to 3 to 4 to 5 and beyond. Okay, so that's called the index of the root. Okay, and we'll just call it n for now. Now this symbol, the root symbol, is called a radical. And the stuff inside of the radical is called the radicand. All right, so we've got 3 terms for you to be familiar with and comfortable with. I'm going to talk about them often. Index of the root, yeah. Radical symbol, yeah. And radicand, the stuff in the radical. Great. Now I'm going to help you with your nth roots a little bit with this table that I'm inputting into your notes. So this helps you know, not just perfect squares or perfect cubes, but perfect fourths or perfect fifths all the way up to 5 in this table, and to negative 5 in this table. So let's break it down really fast and say, hey, if I have some number n, like let's make n 1. Well, if I take 1 and square it, I get 1, and if I take 1 and cube it, I get 1, and 1 to the 4th is 1, and 1 to the 5th is 1. The idea is, no matter how many times you multiply 1 by itself, the result will be 1. What are the powers of 2? Well, if I take 2 and I square it, I get 4, and then, if I cube it, I get 8. If I raise it to the 4th power, I get 16. If I raise it to the 5th power, I get 32. All right, these are the powers of 2. What are the powers of 3? Yeah, like 3 squared is 9, 3 cubed is 27, 3 to the 4th is 81, 3 to the 5th is 243. Powers of 4, 4 squared is 16, 4 cubed is 64, 4 to the 4th is 256, 4 to the 5th is 1024. Powers of 5, 5 squared is 25, 5 cubed is 125, 5 to the 4th is 625, and 5 to the 5th is 3125. So these may be values that you end up seeing in this chapter of notes that we're doing. Great. Well, what if I make these values negative, right? Here I'm making all of them negative, and then I'm going to square, cube, raise to the 4th power, raise to the 5th power. What you notice is these values are the same as these values here in this table, except for one difference. When you square a negative number, the result becomes positive. Okay, when you raise a negative number to the 3rd power, the values are negative again. When you raise a negative number to the 4th power, those values are positive again. And if you raise them to the 5th power, wait, they're negative again. The idea here is if you multiply a negative number by itself an even amount of times, the result is positive, right? So even powers, like n squared into the fourth, result in a positive answer. And then, odd powers, right? Multiplying a number by itself an odd amount of times results in a negative result. So here's like n cubed, odd power into the fifth, odd power, right? So we got negative results here. All right, now, we could call that number x. We're going to see that a lot. We're going to have variables in the mix. And so, if I take x and I square it, it's x squared, x and cube it, x and raise it to the fourth, raise it to the fifth. We could even take the number and call it x squared. And if we square x squared, that's x to the fourth. And if we cube x squared, that's x to the sixth. And if we raise x squared to the fourth power, that's x to the eighth. And if we raise x squared to the fifth power, that's x to the 10th. Just think of multiplying the square by whatever power you're raising it to. Great. So this is potentially useful to you as you proceed forward, especially these fourth and fifth power lists, because we haven't discussed that in this class up to this point. Great. So now I'm going to show you that we can have an index value of, a third, right? That's a cube root, we call it. This is a fourth root. This is a fifth root, right? So we can change the value of the index. You're used to it being a square root where the 2 was invisible, and now we have index values higher than 2. They become visible. They will always be visible. Great. So let's answer example 8.3. What is the cube root of 64? So thinking about this from our table, like I'll just refer to the table here to help you. The cube root of 64, well, if I went to 64 on this list, right, for the perfect cubes, right, I'd have this right here. And so I say, well, the cube root of 64 is 4, right? So you could think of it like this. I'll do it in blue. You could say the cube root of 4 cubed, right? And that'll help your brain see that, the cube, the index of the radical and the power can cancel each other, and the result is just 4. The cube root of 64 is 4 because 4 cubed is 64. All right, so what is the fourth root of 81? So maybe I go to my fourth power list, right? Because my index, fourth power, I go to 81. Well, the fourth root of 81 would be 3 because 3 multiplied by itself 4 times is 81. I could write this as the fourth root of 3 to the fourth to help my brain, right? Because 81 is 3 to the fourth. And then my index cancels the power, and my result is just 3. Awesome. Well, what is the fifth root of 32? Well, my brain would think of all the powers of fifth power options, and I'd go to 32 for that fifth power option, and I'd go left over here, and I'd say, what was that number? Well, it's 2. The fifth root of 32 is 2, and here's why. You could write it as the fifth root of 2 to the fifth, because 32 is 2 to the fifth. And then your brain could say, well, the fifth root index cancels the fifth power. They're inverse operations, and so the result is 2. Awesome. Now, let's play with some ideas when it comes to having negatives inside of a root. Now, like we said earlier, you can't have a negative inside of a square root, but that is the case for all even roots. Okay, so the index could be, if it's even, 2, 4, 6, 8, 10, etc., even index, then you can't have a negative number inside that root, or it'll be no real solution. If that's the case, you've got no real solution. But that doesn't happen for odd roots. If the index value is 1, 3, 5, 7, 9, etc., we don't have that issue that comes up, okay? So I'm going to show you that if I take the cube root of negative 125, I could go over here on this list, and I could say, I'm dealing with an index of 3, so I'm thinking in cubes, and I go down to negative 125, and the cube root of negative 125 is negative 5, okay? And so I'll help your brain think this through. I have the cube root of negative 5 cubed. All right, negative 5 cubed is negative 125. We just saw it on this list. Negative 5, when I cube it, it's negative 125. So I can write this as this, and then you can see that the index of the root cancels the power in the root. And so my result is negative 5. Done. Let's try another. This says the negative fourth root of 16. Well, the negative in this case is in front of the root, so I don't have to worry about the fact that it's an even root. That negative, if it was inside, I would say no real solution. But it's outside, so I don't have to worry. So I say, well, the fourth root of 16. For me, I would go in this list to the fourth power, right? And I'd go to 16, and I think back, oh, 2 to the fourth power is 16, so the fourth root of 16 is 2. But to make it really clear, I'd turn 16 into 2 to the fourth, and I'd cancel the fourth index with the fourth power, and then I'd say my result is 2, but there's one detail. We have a negative in front of it, so I'll put that negative at the beginning of my answer. Yes, so this negative is there, it's still there, still there. Done. Lastly, I have the fifth root of negative 243. I see a negative in the radical, but it's an odd index power, so I'm good to go. I'm not worried about it. It's not going to provide a non-real solution. And so thinking about this really fast, I might take you over here to a fifth power and look up negative 243 in that fifth power list. There it is, negative 243. And that number raised to the fifth power is negative 3. Negative 3 to the fifth is negative 243. And so maybe I rewrite this as the fifth root of negative 3 to the fifth. And then you'll see the index of the root cancels the power inside, and I get negative 3 as my answer. Great, so we have just talked through how to take, cube roots, fourth roots, and fifth roots, with all positive values in this case, and then cube roots, fourth roots, and fifth roots playing with negatives in the mix. Let's now discuss estimating and approximating roots. So in example 8.5, we're asked to estimate each root between two consecutive whole numbers. And this one says the square root of 105, and this one says the cube root of 43. And your brain, like mine, would say, well, 105, that's not a perfect square or a perfect cube. And 43, that's not a perfect cube. Because, here, remember, if the index is invisible, we can make it invisible too. This is a square root. So 105 isn't a perfect square, and this is a cube root. 43 is not a perfect cube. But we can estimate its value between two integers by thinking of the perfect square that's less than this value and the perfect square that's more than this value. And I'll show it to you, right? So we know our perfect squares. Like this value is sandwiched in between the square root of 100 and the square root of 121. Let me show you perhaps here that I just looked at two perfect square values, like 100 and 121. 105 is in between these perfect square values, okay? So when I square root 100, I get 10, and when I square root 121, I get 11. So when I square root 105, I should get a value that's somewhere between 10 and 11. That's what my brain is thinking, okay? So I know that the square root of 100 is 10, which is less than the square root of 105, which is less than the square root of 121, which is 11. So I'm going to estimate that the square root of 105 is somewhere between 10 and 11. I'll write a sentence. The square root of 105 is between 10 and 11. Great. All right, well, let's try this exercise for cube roots, right? So here I have the cube root of 43. Can you think of two perfect cube values, one that's less than 43 and one that's more than 43? Okay, and so we've thought of it, and we thought, hey, the cube root of 27 is less than the cube root of 43, which is less than the cube root of 64. And you're the one that has to decide this, but I'm going to show you really fast that 27 and 64 are perfect cube values that are consecutive, right? So going right here, I have 27 and 64, and the value 43 is right in between them. Great. So the cube root of 27 is 3, and the cube root of 64 is 4. So I know that this value, the cube root of 43, I can estimate it, right? I'm estimating that it's between 3 and 4. I'll write a sentence. The cube root of 43 is between 3 and 4. Great. This is a useful skill because sometimes the value under a square root is not a perfect square, and so I can use this perfect square before it and the perfect square after it to estimate that that value is somewhere between this. That helps my brain. I'm like, the square root of 105, it's got to be a value between 10 and 11. And then in this case, the cube root of 43, it's got to be a value between 3 and 4, right? Because it's between this value 43 is between the perfect cube values of 27 and 64. Great. Please make sure you know these perfect squares, perfect cubes, and you're comfortable with them so you can do these exercises. Moving on, let's approximate, and we're going to round to 2 decimal places. When you're asked to approximate a radical, okay, that's when you can get out your calculator. That's a great time. This is the first moment today where we're getting out a calculator. Great. So the square root of 17 is a value, that 17 is not a perfect square, but 16 is and 25 is. And the square root of 16 is 4 and the square root of 25 is 5. So I know that this is a value between 4 and 5, but I'm actually going to get out my calculator and I'm going to figure out what it is rounded to 2 decimal places. So here I'm going to actually go to my calculator and I'll show you square roots. So I need to take the square root, and the square root symbol button is above the x squared, right? So I go second, and then I click on this button, square root. There's where the square root button is. And I'm taking the square root of 17. I hit enter, and I want a decimal version. So I click the double arrow symbol above the enter sign right here, and it gives me 4.12. Okay, so I now know that the square root of 17 is 4.12. I'm going to write that, 4.12. That's an approximation. It actually is a value that goes on forever. It's irrational. When you take the square root or any root of a number that's not a perfect square, perfect cube, perfect fourth, that number is irrational. It's like pi. It goes on forever, but they told me to round to 2 decimal places. All right, well, let me try another one, the cube root of 49. You're probably asking, how do we type a cube root in the calculator? I'm going to show you. So to type a cube root, there's a button called an X root button. So it's above the caret symbol. I'm going to click second, and then I'm going to click on this X root button. Okay, that'll give me an X root, but first I need to type the index value before I do that. So I'm going to show you, I'm going to type the index value. This is a cube root, so I typed 3. Now I do second, and now I click on the X root button right there. Now I'm being asked to find the cube root of 49. Okay, so the cube root of 49 is what I want. I type in 49 and I get my answer. So this is, once again, a number that goes on forever, but I'm rounding to 2 decimal places, so I will answer 3.66. Be sure to round correctly. Okay, so 3.66 is what I get from my approximation. And the fourth root of 51. So let's reset. I know I'm going to have a fourth root, so I put the index value. That's a fourth root, 4. I click the second button, and then I click the X root button. Okay, now that's the fourth root of 51. So I'm putting 51 under the fourth root, and I get 2.67. Great. So I've just trained you on how to find, type square roots, cube roots, fourth roots, and now you know any type of root, how to plug them into your calculator if you have to approximate some values. All right, so we've now reached the point where we've dealt all in numbers, radicals with numbers. Now we're going to talk about radicals with variables. So our next objective is to simplify variable expressions with roots. And there's one thing that you need to know to proceed, and that's that the square root of x squared is equal to not x, but the absolute value of x. All right? So we don't know whether x was negative or positive, but when you take a negative number or a positive number and you square it, it becomes positive, and then when you square root that, it could have been a negative or positive number, and that's why we're saying that this is equal to the absolute value of x. Now we only have to worry about absolute value symbols when we've got an even root. Okay, that's a root with an even index value, like in this case a 2, right? But that's the same case for index values of 4, 6, 8, etc. We don't have to worry about it when it's odd. So let's go ahead and look at this, simplifying variable expressions with higher roots. So the nth root of x to the n is equal to the absolute value of x if n is even, and the nth root of x to the n is equal to x if the n is odd. Okay, so if we've got an even index, and we got the same power here, that's the absolute value of x. If it's an odd index, an odd power, well, then it's just x. We don't have to worry about the absolute value symbols. Great. Now we're ready to proceed, and we're going to start nice and easy. Asking, what is the square root of x squared? And if it helps you to remember, the square root's the one with the invisible index of 2. If it helps you to put the 2 in, that's great, because you'll realize that this is the square root of x squared. The index of the root and the power of the variable, they cancel each other. And so the answer is just x, but there's an absolute value around it, right? So this answer is the absolute value of x because we were handling this case right here. This was the case. Let's try another. The cube root of n cubed. Well, this is an odd root, an odd index. So all I have to do is say the answer is n. The cube root and the cube cancel each other. I don't have to worry about the absolute value symbol. Kind of cool. All right, let's move on. And we've got the fourth root of p to the fourth. This is an even root. And so you'll understand why my answer is the absolute value of p. Not just p, the absolute value of p, because we had an even index. Moving on to the fifth root of y to the fifth. This is an odd index, an odd power. So yeah, I just have y. That's my answer. No absolute value needed. All right. So be careful, because if we're dealing with even roots, we've got absolute value symbols. Okay. And so we see them there and there. Odd roots, hey, life's easy. We don't have to worry about it. Let's try some more. So I have the square root of x to the sixth. I'm going to put my invisible index right here. I'm just going to do it. Okay, so it's a square root. It's got an invisible index of 2. Now, one cool thing is that you could take this value here and divide by the index value, and it gives you your result. So the square root of x to the sixth is x to the sixth divided by 2, which is 3. Okay, so I got x cubed as my answer. Great. Now, there's only one issue. Because it was an even root, okay, I had to answer that this thing has an absolute value symbol around it. So this is the absolute value of x cubed. Let's try another. So here I have the square root of y to the 16th. Yeah, and you could do the same trick. You're thinking, hey, this is y to the 16 divided by 2, which is y to the 8th. All right. And so you get that as your answer. And you think for a second, do I have to put absolute value symbols around it? The answer in this case is no, because y to the 8th will be a positive value. Okay, you don't need the absolute value symbols. So this is the answer. Let me explain. In this case, your answer had an odd power. So x could have been negative or positive. In this case, y had an even power. So y to the 8th power is positive no matter what. So there you go. Let's proceed forward. We have the cube root of y to the 18th. And to make it easy for you, I would just tell you, hey, you could take y, raise it to the 18 divided by 3 power. So take that power, divide it by the index. That's the easy way to get it done. 18 divided by 3 is 6. And since this was an odd index, I don't have to worry about absolute value symbols again. I'm done. That's my answer. All right, let's look at this next one. This is the fourth root of z to the 8th. So I take 8 and divide it by 4, and I get 2. So the answer for this is z squared, right? Z to the 8 divided by 4. Take this power, divide it by the index. That's the easy way to get it done. By the way, if I take any value, whether it's negative or positive, and I square it, it'll be positive, so I don't have to worry about the absolute value symbol. Right? Even power, no absolute value symbol needed. Let's move on. We've got 16 times n squared under a square root. Right? So I'll put that square root right there. And now I have like two pieces to think about here. And I want to help you guys and show you that this is the same thing as the square root of 4 squared times n squared. My brain sees a perfect square. 16 as a perfect square, it's 4 squared. And then I have n squared. So rewriting it like this can be very helpful. Okay. And when you have the product of two things in a square root, you can apply the square root to the first thing and then the second thing. So what is the square root of 4 squared? Well, it's 4. And what is the square root of n squared? Well, it's n. You could just think of taking 2 divided by 2, right? To get 4 to the 2 divided by 2 is 4 to the first, and n to the 2 divided by 2 is n to the first. But there's one issue. This was an even root, and so I have to take that variable and I have to wrap the absolute value around it. So I have to make the absolute value of n, since n to the first power is an odd power. Okay, so the numerical values never go inside the absolute value symbol. They always go in front of it. They're always multiplied in front. So just the variables are what go inside of the absolute value symbol in these cases. Let's look at the next example. I have the negative square root of 81 times c squared. So I'm going to help your brains. First of all, the index is 2. It's even. I've got a negative out front. Okay, that's safe. I don't have to worry about that. It's just going to continue to be part of my answer. And then 81 is a perfect square. It's 9 squared. And then I have c squared, right? Okay, so let's go ahead and go through the process of simplifying this. I'm going to take 9 squared and take that power of 2 and divide it by 2. Yeah, that just becomes 9, right? I'm going to pay attention to this negative sign. I'm just going to continue putting it as part of my answer. And now I have c squared, right, taking its square root. So 2 divided by 2 is 1. This is just c to the first power. Good to go. But because this is c to an odd power, and it was an even radical, even index, I'm going to wrap c in absolute value symbols. And I'm done. Okay, so this is my answer, -9 times the absolute value of c. All right, let's take it further. We have the cube root of 64p to the 6th. Now, let's go ahead and think of it this way. This is the cube root. Okay, so the index is 3 of 64. Now, remember, 64 is 4 cubed. So I'm going to rewrite 64 as 4 cubed. Now, it's also 8 squared, by the way, right? 64 is 8 squared, but we've got a cube root, so I'm not thinking in squares, I'm thinking in cubes, perfect cubes, 4 cubed. And then I've got that p to the 6th. Now, to make your life easy, just think of taking each piece and take that power and divide it by the index value, since everything's multiplied in here, right? So we have product of stuff. So I'm just going to say, well, 4 to the 3 divided by 3 is 4 to the first. That's my answer there. And p to the 6 divided by 3, 6 divided by 3 is 2. So I get a p squared. Now, because this was an odd index, I don't have to worry about an absolute value symbol at all. No worries. All right, let's try another. The fourth root of 16 times q to the 12th. If I were you, I would rewrite this as the fourth root of, well, 16 is 2 to the 4th, right? We're thinking in powers of 4. So 2 times 2 times 2 times 2, that's 16. So I'll rewrite this as this, and then I've still got the q to the 12th. But I can rewrite this as 2 to the 4 divided by 4, right? So exponent divided by index becomes 1, 2 to the first. And then q to the 12th divided by 4. 12 divided by 4 is 3, so I get q cubed. Q cubed. Great. Now, because I had an even index and this power that results is odd, that's when I'm going to apply an absolute value symbol to the variable, right? The number never gets the absolute value. It's always multiplied in front of the absolute value. So this is the result. All right, let's increase the complexity slightly. And now instead of one single variable, we're going to put 2 variables in there. But you're going to see it's all the same. So I see the square root of 36x squared y squared. And I'm going to rewrite that so you guys can see that this is the square root of 6 squared, right? Because 36 is the perfect square of 6. It's 6 squared. And then I have that x squared and y squared like this. Great. And so now I'm going to, simplify 6 squared. The index is 2, so the result is just 6, right? 2 divided by 2 is 1. I just get 6. And then I have x squared, and then I take that second power divided by 2 becomes 1, x to the first. And then same thing with y squared, 2 divided by 2 is 1, so I just get y. But I have to stop and think because I had an even index and my resulting powers are odd, x to the first, y to the first, they're both odd. I need to put an absolute value symbol around x and y, right? X times y. So that's my result. Remember that numerical value never goes inside the absolute values. The absolute values are only with the variables because we don't know whether those variables are the negative or positive version. Okay, there's our answer. Let's try another. Here I see another square root. And so I say, okay, this is the square root of 11 squared, right? 11 squared is 121. So you need to look for those perfect squares. And then I got a to the 6th and b to the 8th. And now let's go ahead and simplify all of this because, the square root of 11 squared is just 11. And the square root of a to the 6th is a cubed because 6 divided by 2 is 3. And then the square root of b to the 8th, well, that's b to the 4th because 8 divided by 2 is 4. So that's b to the 4th. Awesome. Now I stop and I think for a second and I say, well, man, I've got an even index, which means that I have to worry about absolute values. But those absolute values only have to go around the odd powered stuff, not the even powered stuff. So my final answer is 11 times the absolute value of a cubed times b to the 4th. Okay, that was 11 times the absolute value of a cubed times b to the 4th. And the reason the absolute value only went around a cubed was because, well, I had an odd power with a. Because b has an even power, no matter if b was negative or positive, I'd get the same result. I don't have to worry about the absolute value symbols. And lastly, we have the cube root of 64 times p to the 63rd power times q to the 9th. Okay, this is an odd index of 3. I've got the cube root of, well, 64 is 4 cubed, right? I'm thinking in perfect cubes right now because of the index. 64 is 4 cubed. And I've still got the p to the 63rd and q to the 9th. And so writing my final result, I'll, take 4 cubed, cube root, and I think, well, that's 4, right? Because 3 divided by 3 is 1, 4 to the 1st. And now p to the 63 divide by 3, the index value, and, well, that's 21. That's p to the 21st power. And then I have q to the 9 divided by 3, and that gives me a 3rd power. And because this was an odd root, right, odd index, I don't have to worry at all about absolute value symbols in my final answer. And there it is. We have just done all of lesson 8.1. And my hope is that I've taken your brain beyond just square roots to move on to cube roots and fourth roots and fifth roots, etc. The goal is to know your perfect squares, perfect cubes, and some of your basic fourth and fifth powers. Get comfortable just being able to see it. And use your calculator as little as possible. In fact, the only time we used a calculator today was on this example 8.6. All others were calculator free, okay, because we know this stuff really well. Anyway, thank you so much. I hope you all have a great day, and let's continue to learn about radicals over the coming lessons.